Now let's learn about the velocity function. Velocity is the slope of the position function. Change in position versus change in time. So velocity, which is v of t, is ds dt, or s prime of t. It is the derivative of the position function. Right? And so as a derivative, technically, this is instantaneous velocity. If the position function has a positive slope, then velocity is positive, has positive y's. That means we're moving in a positive direction. If the position function has a negative slope, the velocity has negative y's, and we're moving in a negative direction. And I'm going to do this on the next page. I'm just going to read the question there. Let s of t equal t cubed minus 6t squared be the position function of a particle moving along an s-axis, where s is in meters and t is in seconds. Right? So along the y-axis we're in meters, along the x-axis we're in seconds. And all of these questions here are on the next 2 pages, so I don't need to read through those. All right, so number 1, we're going to graph the position function. Well, to graph, we're going to need to factor. I have an annoying little box here. Guess I'm stuck with it. So if I do that, will go away? Yes. All right, so we can factor out a t, actually a t squared, and then we'll have t minus 6. All right, so we have 2 intercepts where t squared equals 0, so t equals 0, and where t minus 6 equals 0, so t equals 6. All right. Won't really make a difference because we're only there's no graph, there's no negative time, so there'll be no graph to the left of the y-axis. But if we were just graphing this function, right, our graph would touch and turn at t equals 0 because we have that 0 is multiplicity 2. But we start right here, so it won't make any difference. All right, so there's our x-intercept, and then the other x-intercept, 1, 2, 3, 4, 5, 6, right there. All right, let's get another value. Let's find out what happens between our 2 x-intercepts. Let's take t of 3. All right, so s of 3 would be 3 cubed minus 6, 3 squared. So that would be 27 minus 54. So negative 27. All right, so actually we cannot go up by 1s, or the graph isn't going to fit. So let's make each worth 2. I'll just label that once. So that's negative 2, and that's positive 2. No, that'll be fine. All right, so won't fit now. Maybe. All right, we got how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nope, we're going to go right off the graph. You know what? Let's make each one worth 3. 3 sounds good. Plus, it'll be easier to graph. All right, so instead, this is going to be 3. Negative 3, sometimes you have to change your mind when you see the graph's not going to fit so well. So we'll make the scale go up by 3. And I like to make the x and y be the exact same scale so it doesn't distort the graph. All right, so now we have, so there's our 2 x-intercepts, 0, 0, and 6, 0. And now 3, 6, 9, 12, 15, 18, 21, 24, 27. Look at that, fits really nicely. And so here's our graph, our skinny, skinny little graph. And then it's just going to keep on going. Right, because it doesn't have any more x-intercepts. All right. Let's see if we can. Yeah, that looks a little bit better. There we go. All right. So we graph the position function. This is s of t on a number line. trace the path that the particle took. Of course, I had to change the scale. I was smart enough not to erase that part. All right, so, and if this is in your notes, then you want to change the scale. I don't remember which problems or which parts in your notes because I don't have the notes in front of me. All right, so let's trace our path. So we're moving in the negative direction till we get to negative 27. So in the negative direction, and we get to negative 20. Oops, well, I usually like to do red for negative. It's probably not a big deal, but let's be consistent. Oops. All right, so we moved in the negative direction, and then the particle, I should say, the particle turned around and moved in the positive direction. And how long? Well, it's going to keep on moving in the positive direction. All right, just keep on moving. All right. All right, so that's what else we need here. We got that one. And when will the velocity be positive and when will it be negative? Now, I had to estimate where it would turn around. I mean, it's possible that it turned around at 4 and not 3. We're going to learn how to find out exactly where it turned around. I will take my approximation here, so we'll just leave it to that approximation. But in the future, we'll be able to find the exact. All right, so where will the velocity be positive and where will the velocity be negative? Right? So velocity is going to be positive so velocity is greater than 0 where s of t is moving in a positive direction. Right, we have a positive slope. All right, so that means from right here, right, and then for onward, right, our particle is moving in the positive direction. So we're moving in a positive direction from 3 to infinity, right? So everywhere here, our velocity is going to be positive. All right, so velocity is positive because the slope of s of t is positive. All right, and where is it going to be moving in a negative direction? Actually, maybe I should put this here. I should have put that answer there. Here, you know what? I'm just going to finish this answer. There. If we put all that there, then we can put our second question here because it's right here where the graph is negative. Right? And actually, we forgot to put the time. So velocity is greater than 0 on the interval of 3 to forever seconds. Right, so right here is where our velocity is negative. So velocity is negative, less than 0, right where we're red here, because the slope of s of t is negative. S of t is moving, actually I should say s of t, the particle really, that the graph doesn't move, the particle moves. Oh, look at that. I can just remove that. So let's change S of t actually to particle. So the particle is moving in a negative direction. And that's happening on the interval. I'll abbreviate a little bit because I don't have much space. So right away it's moving in the negative direction. So let's use a bracket. So 0 to 3 seconds, but then a parentheses, right? Because it has to stop. At 3 seconds it stopped, right? Because it has to turn around. Right, so we've answered all the questions on this page. Let's continue. All right, so let's graph the instantaneous velocity. Right? So to graph the instantaneous velocity, we need to take the derivative. So S prime of t, which is v of t, derivative is going to be 3t squared minus 12t. All right, so let's graph that. We can factor out a 3t, and we'd be left with t minus 4. So this one is nice and easy to graph. All right, so we have x-intercepts at t equals 0 and t equals 4. And then we have our vertex at 2, right, because it's got to be halfway between. Right? And if you add 0 plus 4 and divide by 2, you get 2. All right, so S of 2, we want to find out where, oops, excuse me, make sure I plug in the right thing. Not S of 2, because we're graphing velocity, excuse me, V of 2. That would be 3 times 2 squared minus 12 times 2. Actually, it'd be easier to plug it into this one, into the factored one, but oh well. So that would be 12 minus 12, negative 12. And let me just label this one as V of t. All right, so we're going to, I think we can use a scale of 2 this time. Right, so we have 0, 0, and this would be, actually, can we? 1, 2, 3, 4, 5, 6, 7, 8. Oh, we can have a scale of 1. All right, so 1, 2, 3, 4. And all right. So this time the scale was just 1. All right, so here's our graph. Oops. Whoops. There we go. There we go. So this is S prime of t, which is also equal to V of t. All right, so here we can see when we're moving in a positive direction. And we can actually probably clarify our graph on the other page. So notice that here our velocity is positive. Actually, we'll use the number line. So our graph is, we're moving in a negative direction at first, right? So we move 12 to the left, and then we move forever to the right. Now notice where the velocity changes, all right? So here our velocity is negative from 0 to 4. So that means when we were estimating our point over here, it actually turned around at 4. So let's clarify that. All right, S of 3 was a good approximation, right? It was a good guess, right? We were used to that. We were graphing in algebra 2, right? Estimating between our x-intercepts somewhere we turned around. And 3 was a good choice. However, we now can see from our velocity graph that it was really 4. All right, so that would be Actually, let's plug it into this one. So 4 squared times 4 minus 6. So that's going to be 16 times negative 2. So that would be actually negative 32. So negative 32 we actually turned around. So that means that we were actually moving in the negative direction a little longer than we realized before we turned around and went in the positive direction. All right, let's alter our graph a little bit. So we stopped originally at 27. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So actually we should turn, actually it should be at 4. All right, so this would be a more accurate graph. Of course, it's not that easy to graph 4 in there. And so we can change that 0 to 3, because we can see from our velocity graph that that was really 0 to 4. And if you're getting the thought that maybe the first derivative helps us figure out where a graph turns around, then you would be absolutely correct. So that was 4 to infinity. All right, so we can estimate no more. We can use our first derivative to help tell us where we turn around. Now we can see that at 4 seconds is where our graph changes from negative velocity to positive velocity, thanks to our first derivative here. All right, so moving in a positive direction, I'll just put the answers over here, and then we'll put the explanations over there. All right, so positive direction is from 4 to infinity. All right, we are above the x-axis, and that is velocity that's above the x-axis. There we go. Moving in a negative direction from 0 to 4 seconds, and we stopped at 4 seconds. We had to stop, otherwise we couldn't turn around. You can't like instantaneously go from going in the positive direction to negative direction. You have to stop for a second and turn around. Right? It's impossible to do it any other way. So let's take a look here at what we can learn from our velocity function. All right? Oh, and let me put in here. So here we were moving in the positive direction. All right, so I'll put it up here. So where v of t, which equals s prime of t, is above the x-axis, the velocity is positive. The particle is moving in a positive direction. Also, the slope of s of t is positive. I'll just put it as greater than 0, it's fine. Positive greater than 0. All right, so here, where v of t, which is the derivative of the position function, is below the x-axis, the velocity is negative. The particle is moving in a negative direction. And the slope of s of t is going to be less than 0. It's going to be negative. Right here and here, when v of t equals 0, the particle is stopped. If we look back at our graph, s of t, let me move it up just a little bit. Has a horizontal tangent line. So that is something important to note. All right, so here, and the one that would, so here the particle hasn't started yet. So there wouldn't be a horizontal tangent necessarily here because we don't have any more graph. If we had more graph, by the way, the graph would have touched and turned. So there would be a horizontal horizontal tangent at x equals 0 if we had negative time, but we don't have any graph over there. All right, if we look back here, we can see right here was the horizontal tangent. Right, and that's at t equals 4, which matches our, oops, hit the wrong way. Which matches our x-intercept on the graph over here, right? Where we have an x-intercept right there, t equals 4. Whoops, now I went too far. Of course. Now it just has a mind of its own. Okay, there. Better not change again. Okay, and here it hasn't started yet. It's at rest. So squeeze that in there. At rest. All right, we're going to look at one more thing. And that is velocity or speed. So speed change in position with respect to time in any direction. So where velocity is directional, it's change in position with respect to time in a particular direction. Speed is change in position with respect to time in any direction. Right? It is not directional. Therefore, speed cannot be negative because going backwards or forwards is just a distance. Velocity can be negative because we care if we go backwards. We care if we're going forwards or backwards. With speed, we don't. So speed is just the absolute value of velocity. So if you take the instantaneous speed, the v of t, and take the absolute value, you have speed. So if two particles are moving on the same coordinate line with a velocity of v equals 5 meters per second and v equals negative 5 meters per second, then they are going in opposite directions, but both have a speed of 5 meters per second because we're taking the absolute value when we're looking at speed. And I think that is where I'm going to stop. Yep. All right, so thanks for watching. Bye for now.